In this video, we're going to talk about how we can do something called measure central tendency. Now, that kind of sounds weird, kind of sounds formal. Let me kind of cross it out and say, what is an average result? So that's kind of the question we're really trying to answer here is if you have a bunch of data, let's say you have the number of children in a bunch of different families, what is the number that is average? What is the common amount? What is the type of amount you would expect to see in a usual circumstance? What if I look at the height? What number am I thinking of when I see a random person? What's going to be their average there? Now, you probably say, oh, I don't do average, just add them up and divide by how many there are. And that's right, but that is only one type of average. There are other circumstances that you would calculate something that is different and that may or may not be more useful than the one that you're thinking of as average already. So the adding them up and divide by how many are, that's what we call the mean of the data. And I put there in parentheses arithmetic mean because there are actually other types of means out there in the world. There are things like the geometric mean. There is something called the weighted mean that we will see later. But for right now, the only thing we're worried about is the arithmetic mean. And again, we already said what it was. The mean is just add up all the numbers and divide by how many there are. So that's something you've most certainly experienced sometime in your life before now. Now, with that said, I'm going to give you some formulas now. Now, these formulas mean the exact same thing as those words I just wrote out. Add up all the numbers, divide by how many there are. However, you're going to want to get used to kind of these formulas because you're going to see more and more formulas in this class. Some of these formulas are going to be pretty complicated. They might seem confusing. I sympathize with you, but it's very common just to see formulas and formulas and formulas in statistics class. And I will show them to you and we'll do some calculations with them. But I do want to point out a couple things here. One, I want us to get used to the formulas, but you don't have to memorize them. You never have to memorize formulas in my class here. We'll make sure that you have them available to you during any exams and so on. We just need to understand what they mean. That's what the really point of it is. And secondly, is we're almost never, very rarely going to actually use the formulas to calculate things by hand. I will be having separate videos to show you how to use your calculator to calculate all these things for us. So in these videos here, I might do like a small example by hand and we'll show you how the formula works, but understand that for any serious example of these we want to calculate, let's say 20, 30 data points or something, you're not going to do that by hand. You're going to let a calculator do all the hard work for you. And I will have a separate video showing you for each type of calculation we want to do. I will show you how to do that in your calculator. Now, furthermore, I said these formulas can seem complicated. I mentioned in a previous video we have these things called parameters and statistics. So when you do a numerical calculation for population data, you get a parameter. So population will give us a parameter. On the other hand, when you do a numerical calculation for a sample, you are going to get what's called a statistic. And so technically there are going to be two formulas here. There's going to be the formula for the population mean, using the notation for that. And then there's going to be the formula for the sample mean, using the notation for that. Now, both of them are going to say add up all the numbers, divide by how many there are, but they are going to look different. So here are the two formulas. The formula for the population mean, and I mentioned on the parameter video that we usually use a Greek letter. And so this right here is a Greek letter here. So let's go ahead and write this out. It's the Greek letter mu. And that stands for population mean. And the formula is going to say, do this and then divide by this. Now, I have another Greek letter here. This is the capital Greek letter sigma. Capital sigma. And all capital sigma means is add up. So when I put the capital sigma next to xi, it means add up all the x's, all the values of your variable that you've measured. And then capital N is the population size. And so you add up all the data points, divide by the population size, and that gives you your population mean. We have a very, very similar formula, something called the sample mean. So this is talking about if you have sample data and you want to calculate the mean compared to having population data. And we are going to have a different symbol for it. I know it's confusing, but we have to kind of get used to it. So we're not using Greek letters here for the sample version. We put an X with a little line over it. We read that as X bar. So X bar is our sample mean. And the formula is going to look very, very similar. Add up all the xi's, but this time we divide by lowercase n. And the difference again is the capital N is the population size, how many people are in your whole population, whereas little n is your sample size, how many people did you get your data from. So again, both of these formulas are saying add up the data points, divide by how many there are. But we use different notation so that we can know whether someone's talking about population data or if someone's talking about sample data. And that's very important because, again, as I said in a previous video, we're almost never going to have population data. We're almost always going to have sample data, but we're going to then use our sample data to try to make conclusions about the population. And so we need to be able to separate things between population and sample so we know what is actually something we've calculated and what is something that we are estimating. And that's why we have these different notations here. Okay, so that right there is how we calculate the mean. And that is your normal average that you've seen before in previous classes. You may have also seen these other two here, median and mode. I'll kind of go over them quickly here. So median, this is the middle data point when data is put in order. So let's suppose I have data here. I'll take 1, 7, 13, 15, 20, 23, and 31. Now that's 7 data points and they're all placed in order. So I'd ask myself, if they're in order, what's the very middle value? And you see 15 is the middle value because there are 3 numbers to the left and 3 numbers to the right. So that means the median would be 15 here. Oftentimes we use capital M for median. That one is not as completely accepted to everyone compared to like the mu and the x bar. Those one everyone uses, but capital M is usually going to mean the median. The only thing you have to be careful with is what if you only have an even number of data points. So let's say I take off that last one. I don't have the 31 anymore, and if I try to circle 15, this is no longer going to work because now there are 3 data points to the left of it and only 2 on the right. That means that's not really the one that is, sorry, let me fix this here. That one is not truly in the middle of all the data. Similarly, what would happen if I were to circle the 13? Maybe that's the middle one now. No, now there's 2 to the left and 3 to the right. So that means it's also not the middle data point. So if that's not going to work, if I want it to be truly in the middle, it's got to be right here, right? Something there would be splitting the data into left and right. But the thing is, there's no data point there. So what we're going to do, whenever you have an even number of data points, just take the one that's right to the left of the middle and the one that's right to the right of the middle, and you're going to take the mean, the average of those two, and that would become your median. And now there are 3 data points to the left of 14, 3 data points to the right of 14, that is my median. So whenever you have an even number of data points, you have to do an extra step here. Whereas if you have an odd number of data points, just pick the middle data point and you're good to go. Okay, last one here is the mode. So the mode is the most common data point. That wouldn't really make sense with the previous data because everything occurred once. But let's say you have data where sometimes a number will occur more than once. So here's a bunch of data there. You see the number 1 occurs twice, 2 only once, 3 twice, 4 3 times, 5 once, 6 once, 7 twice. So in this case for the mode, you just look for whichever one happened the most often, which is 4 here, because there's 3 of them. And that means your mode is 4 for this data. Now sometimes there is a tie. So if there is a tie for the most common data value, then it is bimodal if there's 2 different modes, or multimodal. So it can happen where you have 2 different or more than that different common points, and we just give that a name of either bimodal if there's 2 different data points that are common, or multimodal if there's more than 2 different data points that are common. So these things can happen. Mode is actually going to be the one we're hardly going to use in this class. It is used sometimes, but just not very much. Median, we'll use it occasionally, certainly more than the mode, but not that much. We're mostly going to use the mean because that's the one that a lot of math is going to work out well for later in this class. So we just stick with the one that things work out nicely. But I do want to point out that there are reasons why you might want to use one over the other here. And so this last thing here is talking about resistant measure and shape of distribution. So we talked before about if you have, say, a bell-shaped distribution. Well, in this case here, your mean is going to be approximately equal to your median. So your median data value is going to be about what the average is, the mean average. So everything's great there. However, if you had, say, data that was right skewed, what ends up happening generally is that the mean is bigger than the median. So your mean, if you look at your data point that's kind of in the middle of data points, it might be, somewhere around here, maybe a little bit to the right, but your mean is going to be somewhere further right because those large data values, they're going to skew the average, the mean, to the right here, and this is going to cause a problem. And similarly for the left skewed, in that case, the mean is going to generally be less than the median. And so what ends up happening is when you have these data that are really, really big or really, really small compared to what's normal, the common scenario, common values, it's going to skew the mean there, but it's not going to affect the median too much. And if you look back up here, let's say, here we had our data value there, and we got a median of 15. Well, if that last data value, instead of 31, what if this became, 31,000? That's a huge number that would really mess up your data when you were calculating the average, but it would not affect the median at all. And so what we do is we say the median is resistant to extremely large or small data values. So it's resistant to changing. So if you take one of your data values and make it, way, way larger, your median's not going to really be affected, but your mean would not. So mean is not resistant. it is affected by these very large values here. And so whenever you have data that is skewed, a lot of times you will use median to describe it rather than the mean. And I challenge you right now, go look up, say, average income in Orange County, or look up average home price in Orange County. I guarantee you they're not going to be giving you data with the means, because those are right skewed data and the mean would be skewed and it wouldn't be very representative. They almost always use median for that because it's a more realistic measure of what the average might be in that case. So anytime you have skewed data, mean is probably not the best choice to use to describe what's going on. However, if your data is bell-shaped, mean would probably be just fine to use to describe your data. So it really just depends on what scenario you're in, which one you want to use. But for this class, as I said, we're learning all of them now, but in future chapters, the one we're going to use by far the most is the mean, because that's going to make all of our math work out well, all our results work out well. And if you wanted to actually focus on the median, you could, but those are kind of more advanced techniques that we don't learn in this class. So